Welcome to the Building Better Batteries webinar series that is sponsored by Thermo Fisher Scientific. My name is Christina Pogge. I'm Senior Manager for our Science and Industry Content Strategy team at Wiley, and I will give you a quick overview of what you can expect to learn today and in the coming weeks. This is an 8-part webinar series that explores the intricate process of battery development, from materials research to cell manufacturing. This series aims to identify unmet needs and prevent failures while maintaining high-quality assurance standards. You learn about essential topics and ensure the quality and longevity of batteries, gaining insights into advanced techniques and methodologies, while diagnosing battery issues, understanding failure root causes, and implementing preventive strategies. Today, we will be presenting 2 analytical solutions for manufacturers that are looking to assure the quality of battery electrode powders and electrolytes. First, Weihui will review imaging characterization and analysis techniques for lithium-ion battery failure analysis. We will then move on to Hernan Sanchez of Exponent. He will talk about the roles of destructive and non-destructive characterization in battery failure analysis. Finally, we will end with Sudhir Dahal, who will review vibrational spectroscopy for battery component characterization and analysis.
As a company, Thermo Fisher Scientific has a clear mission: to enable our customers to make the world healthier, cleaner, and safer. Let's break that down a bit further. Healthier. Thermo Fisher Scientific contributes to human health by empowering our customers with advanced technologies and expertise. This allows them to develop breakthrough medicines and diagnostics that improve lives across the globe. From life-saving treatments to innovative diagnostics, our customers rely on us to help them achieve the impossible. Cleaner. In the fight against climate change and environmental degradation, Thermo Fisher Scientific provides the tools to understand these challenges and develop greener solutions. Our technologies help ensure the quality of air and water, essential elements for life on our planet. Together with our customers, we are committed to preserving the environment for future generations. Safer. From detecting contaminants in food to solving crimes and identifying threats, we help our customers protect their communities. Our instruments and solutions are designed to keep people safe, and together, we are determined to make the world a safer place. At Thermo Fisher Scientific, we are not just creating products. We're enabling our customers to make an impact on the world. Thermo Fisher Scientific is the global leader in serving science operating in 170 territories with over 140,000 colleagues, generating over $40 billion of revenue, and they reinvesting almost $1.3 billion annually in new products. Within the battery market, Thermo Fisher Scientific partners globally to deliver advanced integrated solutions from the research laboratory to the battery production line that ensure material quality and accelerate improvements in battery production efficiency. Thermo Fisher Scientific serves the battery value chain with advanced analytics from research to recycling, with market-leading technologies in spectroscopy, electron microscopy, and mass spectrometry. Within this webinar series, we will be focusing on the mining and mineral processing, battery component materials QC, and production pieces of the battery manufacturing value chain. There are many dynamics affecting the battery industry. Firstly, to compete in the battery marketplace, new battery manufacturers need to get to high yield, high volume manufacturing fast. Poor quality costs material, production volume, and time. You must prioritize quality. Saving money on metrology is seldom rewarded with anything but headaches. Companies are prioritizing quality. Secondly, new battery companies are investing in innovation. There's little chance to catch up with established battery manufacturing companies in China by repeating what they do. Companies are looking to leapfrog. They are investing in advanced technologies early to facilitate faster product development and troubleshooting of quality failures. Thirdly, new battery companies are thinking globally. They may have a laboratory and pilot line in Mumbai, but they will want to replicate that capability as they scale their operations in Europe and North America. Consequently, they need global partners who can support their growth in every territory.
Our speakers today include two speakers from Thermo Fisher Scientific, Weihui, a market development manager within the Clean Energy Group, and Sudhir Dahal, a product manager for vibrational spectroscopy. We also have Hernan Sanchez, a principal scientist from Exponent. And now I will hand it over to Weihui.
Welcome to my presentation today. My name is Weihui, the Market Development Manager in Clean Energy. Today, I'm going to talk about imaging characterization and analysis techniques for lithium-ion battery failure analysis. Before I get started with it, let's talk a little bit about the scope of lithium-ion battery failure analysis. When you are manufacturing a lithium-ion battery, the main element may include material, structure, design, and the process, which eventually decide the electric performance, safety, and reliability of a battery. During the whole life of a battery, there will be different kinds of failures in different stages. What I want to emphasize is that when discussing the relationship between battery failure and the interplay of materials, structure, and process in lithium-ion batteries, it's very important to adopt a holistic perspective. So it will require comprehensive analytical characterization. The failure of lithium-ion battery is rarely attributed to a single factor. Instead, it's the result of complex interactions, as we all know, occurring at various scales and involve different mechanisms. And you all know these reactions can be broadly categorized to electrochemical and chemical and the mechanical process, each occurring at different scales, ranging from atomic to micro levels. And battery failure analysis is a systematic approach that follows a logic flow from non-destructive level to destructive method, and from cell level analysis to extrude and material level investigations. And this comprehensive approach ensures a thorough understanding of failure mechanisms at various scales. Then I would like to talk about how electron microscope provides to failure analysis and how to review root cause of battery today. And we know typical failure modes of lithium-ion battery includes low capacity, cycle capacity fading, self-discharging, high impedance, and safety issues like thermal fires or explosions. And always CT computed tomography scanning is always a critical tool in battery failure analysis due to its non-destructive nature, and it allows for the internal examination of the battery without causing any damage and perceiving the integrity of the sample for further analysis. And the objective of electrode level analysis is to understand the connectivity and structural integrity of the electrode, which always may include characterizing cracks in a large view, clogging of pores or connectivity of active particles, and the black spots on electrode and some others. Usually pinpointing failure locations is required when conducting regional electrode defect like black spots analysis, which may indicate localized degradation or contamination. And the objective of material level analysis is to focus on material degradation and loss mechanisms at particle level, which may include structure degradation, micro crack, exfoliation, and metal dendrite and SEI degradation. And today, I'm going to talk about unveiling electrode degradation for insight into cell failure, pinpointing the defect in terms of doing site-specific analysis. And last, we are gonna wrap up with a kind of correlative microscope solutions to bridge the length scale from micro-CT data in a non-destructive analysis so that we can find a defect and use our dual beam to characterize the defect. So let's get started with the identification of crack in cathode material. Particle cracking in cathode material is a significant factor contributing to capacity fading in lithium-ion battery. Repeated charging and discharging cycles may cause volumetric changes in cathode particles and lead to mechanical stress and eventually cracking of active particles. The crack could lead to loss of active particles by isolating portions of active materials and disrupting of conductive pathways within cathode, increasing internal resistance and exposing new surfaces to electrolyte, which can lead to unwanted side reactions and eventually lead to the capacity fading of the battery cell. And using Thermo Fisher clean mill broad iron beam, we can get a nicely prepared large cross-section of cathode electrode without exposing to air due to its capacity with our clean connect inert gas sample transfer system. And then using Thermo Fisher April chemism for imaging the cracks or the cross-section at a really excellent fast imaging capability. And finally, we always want to know how many cracks across the cross-section of electrolyte. And however, it's always hard and sometimes boring for battery workers to analyze those cracks without an automated and statistical way. So the need is always to do this kind of work in a fast, reliable way, like an automated way to get the statistical result of crack. We provide a system, as we mentioned last page, to make a non-site specific cross-section with mill and get the images of cross-section quickly with April chemism. Also, we have a methodology to process the image and quantify how many cracks existing with a visual throughput software. And this is a dedicated application that's built specifically for battery scientists and engineering to be able to do automated image interpretation. The whole workflow should be SEM provide high-resolution images of the cross-section of electrode and allowing visualization of particle cracks. And the image analysis software, a visual throughput, can be used to measure the size, distribution, and density of defects such as crack. It turns Thermo Fisher SEM into an automatic solution, helping you to minimize the efficiency, maintain the quality standards, and achieve operational excellence. Simply acquire image and select automated analysis. Then you will get the report with crack distribution information. Although traditional 2D characterization techniques such as we have already mentioned the SEM with BIB for sample preparation can provide plenty of insights from cross-sectional structure however, the 3D imaging techniques is always needed in battery failure analysis as well. And before I talking about it, I would like to show you a video. Here, we introduce our dual beam technique. If we go into the microscope, we can observe the sample with SEM. Then the red beam we can see is actually cutting away materials and sputtering away materials with focus on B. In this particular example, we are able to take all these images and make a 3D rendering or do 3D reconstruction of that sample. But if we just want to expose one section of the sample site specifically, a dual beam does that quite well. This shows how it's done. As we already mentioned, although the 2D characterization techniques such as SEM with BIB for sample preparation, as we already mentioned, can provide plenty of insights from cross-sectional structure to battery failure. When evaluating the complex interconnect nature of the different components and variation during recycling, a 3D imaging characterization and analysis is always needed. And this approach provides a comprehensive understanding of the internal structure and the interactions within the battery, especially for cells with thick electrodes. And if you look at this use case showcasing that battery cycled at a higher voltage experienced heavier capacitive degradation than at lower voltage, particularly in cells with thick electrodes. So always the degradation process in thick electrode is closely associated with structural and chemical complexities at different length scales. Evaluating these complexities requires full 3D characterization. And in this case, we use plasma-focused ion beam to acquire a large 3D imaging volume of thick electrode. And this technology allows for high-resolution imaging and detailed analysis of the internal structure. The images collected through PFIB, plasma-focused ion beam, are reconstructed to create a 3D model of the electrode with a visual 3D software, and then quantifying the cracks and connectivity between NMC and carbon binder domain, here named CBD, through the 3D volume. Then you can compare the impact of this structural information as shown here. The electrode for higher voltage cell experience heavier cracks and disconnections inside the electrode. In summary, PFIB technology combined with a visual software provides a powerful tool for acquiring large detailed 3D images and understanding the structure and chemical complexities that drive the battery degradation. If you look at this use case, micro short circuit in lithium-ion battery, it always refers to the localized failures that can significantly affect battery performance and safety. It can directly lead to fast self-discharging of the battery. It's a very common failure of lithium-ion battery. Please see the schematic here. If Cooper particle present in cathode of lithium-ion battery, then during charging and discharging cycles, the Cooper may experience dissolving deposition and growth in form of dendrite. Eventually, it will penetrate the separator and cause the short circuit or even thermal runaway. After disassembling the failed battery, we often found the black spot or anode or full charged anode, and we needed to find the corresponding location of the separator. It's always difficult for battery workers to pinpoint the defect visually or with an OM or for the separator. We use SEM and we use dual beam to observe and locate the short circuit region precisely and decide where to cut across. Then use the FIB of the dual beam to expose the cross-section of dendrite inside the separator to review how the micro short circuit happened. Look at the image below. The bright contrast inside the separator should be the Cooper dendrite formed during charging and discharging. I would like to share another use case for micro short circuit analysis with dual beam for lithium iron phosphate battery. This should be a high self-discharging battery after dismantling the battery in a full charged state. We did find the suspicious site of short circuit or the full charged golden anode electrode. Then we cut across the site 1 or separator with dual beam and found the pores are blocked. The pores of the separator are blocked in a large area. With the help of energy dispersive spectral analysis named EDS, it is revealed that a kind of material containing iron and fluorine formed and distribute across the separator, which is shown here. It's likely caused the short circuit of this battery cell. I would like to say that the DuraBeam technology provides a powerful tool for high-resolution site-specific analysis, offering valuable insights into such kind of battery failures. So this is my last example. I would like to focus. It's a kind of taking everything all together. I would like to spend some time talking a correlative microscope we have. It allows us to do correlative imaging from computed tomography and bring information to our microscope. You know, manufacturing battery really involves multiple steps to be able to understand what the problems could be if you are seeing performance. As for visual inspection, you probably have to do some analysis from non-destructive perspective to examine any defect inside. Usually, you need to perform a full 3D CT scan of the lithium-ion battery to identify and localize the areas of interest, such as the potential failure sites or structural abnormalities. If you want to deep dive into the mechanism of defect, sometimes you may miss it if you disassemble the sample cell, or you may miss the affected region inside the battery. With the correlative technique, you can easily locate the defect and guide the selection of the specific area for focused ion beam cutting and detailed SEM analysis for microstructure and EDS analysis to determine the element composition. Here we use a V-gate CT to perform the non-destructive analysis of the pouch cell and precisely find the location of the defect as shown in the red circle. If you see this image, we will find that this site is several cathode and anode electrode in millimeter depths from the surface. We achieve the cross-section with femtosecond laser that is available on our DuraBeam tools. We call it tree beam, which allow us to expose really deep features like shown here. Finally, we found the cathode material present in anode electrode. You can move from CT to DuraBeam by using sample holders that allow us to lock to different features at macro scale and then turn those into micro scale so that you go straight to the site-specific locations and make the cross-section with high throughput tree beam tools or DuraBeam tools, or do SEM EDS analysis to understand the mechanism of the failure. And in summary, I would like to say that Thermo Fisher is sure offering a total solution for electrode degradation analysis. For example, BIB, SEM, and a visual throughput can provide fast and quantitative 2D analysis for particle crack. PFIB and Aviso could provide large 3D volume characterization of electrode connectivity for electrode degradation analysis. And the site-specific failure analysis is easily achieved with Thermo Fisher DuraBeam so that we can easily get to the root cause for failure. Complex failure, which require a non-destructive to destructive analysis to interpret the failure from cell to electrode and material level, we offer a solution enabling correlative imaging and the site-specific analysis at a much more accurate and precise way. And there's a lot more offering that we provide for battery science and research beyond the scanning, electron microscope, and the DuraBeams. For nanoscale and characterization, we offer the Thermo Fisher, Talos, and the Alliant system, which enable us to examine atomic structures in detail. And these tools are particularly effective for characterizing the solid electrolyte interface SEI layers. If you're interested in component analysis like active material, phase degradation, or atomic defects, these systems provide a robust solutions for characterizing those materials. Besides, we offer surface analysis, XPS, a crucial solution for understanding the surface chemistry occurring within battery components. And lastly, I would like to highlight that while not specifically a failure analysis technique, we also offer dedicated SEM EDS systems for quality control purposes. These systems are valuable for particle analysis, allowing for detailed examination of component consistency and impurity characterization. Okay, thank you for your time and attention today. It has been a pleasure sharing this kind of battery information with you. I'm happy to take any questions you may have.
Hello, everyone. Thank you for having me. I will be following up on that fantastic talk that we just had with additional discussion about battery failure analysis and the role of both destructive and non-destructive testing. So very much in line with what we were discussing before. And the idea is to discuss kind of like when you should be in failure analysis, quality assessment, and battery performance testing to understand when you should be using non-destructive and destructive techniques. So first, a little bit about me. My name is Hernan Sanchez. I'm a principal scientist at Exponent. For those of you that don't know Exponent, Exponent is a global multidisciplinary consulting firm that is dedicated to solving important problems in science, engineering, health, and regulatory issues. But for the purpose of this talk, we do a lot of work with batteries. We usually work globally across with our clients, and that can be either from litigation support as expert witnesses or in IP litigation work, or it can be more on the what we call proactive side, which is design consulting or risk management or just help with product and process improvement. In the battery world, if it's in the news and there's a technical component, we've likely been involved. There's been ESS fire investigations, now a few years back, the Note 7 recall, and then we do a lot of work with micromobility. So all of them battery failure related, and we do a lot of work about that. So, and once again, my company broadly works on all sorts of problems, not just batteries. It can be from electrical failures to polymers, adhesives, and other things. But within the battery realm, we have almost 80 scientists and engineering that focus on that work. We have hundreds or more than 1,000 publications. We come at it for any of these problems with a multidisciplinary approach and over 20 plus years of battery experience. So and that's kind of like what I'm going to talk to a little bit, using that knowledge and that experience to describe a little bit about this. When you have the failure analysis investigation showing whether it was a internal cell fault or user induced, or like using a quality assessment to provide feedback for cell design and manufacturing. The ability to understand a battery via both destructive and non-destructive techniques can provide benefits to making the product safer and more reliable. So I've broken this talk into 3, and just mostly case studies or cases that are inspired on real cases that we've dealt with in the past, and those are I've broken them into purely failure analysis investigations, more battery quality assessment, and performance evaluations. The failure analysis, and there was there were some very nice slides about that. This talk is like when things go thermal, right? Like that is at the end of the day the worst case scenario and what you want to prevent. But when it happens, you need to understand why the failure took place, right? For those of you that have not been very much involved in like a failure analysis of a burned battery, usually what we prefer is what we like this outside-in approach, which involves not just looking at the cell, but looking at things before that, like right from device background information, if it's a new device, if it's an old device, if it's been repaired. Also information from the scene of the failure, like fire investigation reports. We have our own fire investigators that sometimes assist with those investigations ourselves. Then from there, you move into the device to understand to see if there's any signs of damage to the device or any signs of like oxidation, corrosion. So those are all things that we look into it. And then if all this evidence is pointing towards the cell, then we start looking into the cell. And this is where it comes down to the techniques that were being discussed before in the previous talk, which once again, non-destructive and destructive techniques involving CT scanning, and then a lot of things that you can do afterwards, after you've done that non-destructive step, which is, like cell teardowns, cross sections, and a lot of SEM EDS. So to give some examples of how we apply this methodology into real case examples, and also when we do what happens at each step of the destructive and non-destructive. So, this is a typical case that we work on. We work on hundreds of this probably a year, and it's like power tools. And when there's been a fire, there was a power tool in the garage or in the wherever it was. First, we get all that information I was mentioning. In this case was an old battery pack, and it was not charging, and it was not in a tool. So that already was something I like. Oh well, people are claiming this is the battery, but let's look a little bit deeper into it. So first step, once again, the non-destructive CT scanning is very powerful because it lets you look inside the cells. In this case, we were able to establish that all 4 cells had experienced thermal runaway. But looking at the CT data, we were not able to find any high density features. And usually those high density features can be correlated with cell short. It's one piece of the puzzle, and all of these investigations are really puzzles, and you go gathering evidence, and with that you come up with the best understanding that you can of the failure mode of what happened, right? In this case, we were not finding any high density features. So with that, we were able to, and now that we have the CT to have the data that stored, we were able to push towards the destructive testing. And in this case, we were able to look at the unfolded cell, and it turns out that we were seeing a lot of missing copper current collector, but all of the edges of that actually had this silvery discoloration. And this is where, once again, being able to use SEM EDS was very powerful, because we were able to determine that these were all signs of copper aluminum alloying. And for those of you that have dealt with alloying and understand phase diagrams and alloying related to that, the temperatures in which you can melt a copper aluminum alloy is much lower than melting pure copper. So once again, this is a piece of the puzzle that tells us that we were not able to find in the remnants anything that told us that the cell had gone over 660 degrees Celsius, which would be what you would need to melt the aluminum and to start the alloying process. Or you can even do it a little bit lower than that too. But we were not talking about temperatures over 1,000 degrees Celsius, which is sometimes what is more associated with an internal cell short. So that, combined with all the other information we were gathering, this example leaned very much towards some type of external heating causing the cell failure. And on the opposite side of that spectrum, this is a case that we also quite a few of these, which is like a computer failing at a user's home. The computer was plugged in, so there was definitely a question about whether something was happening with the battery. And what's interesting though is you look at this device and you see that there's damage to the device but not to the screen. So once again, this is all that outside in looking into the device and gathering clues. And then we were not seeing any obvious mechanical damage to the device interior because there was too much thermal damage. So this is where, once again, CT scanning, first thing we do, we gather that data, we take a look at what looks inside before we do anything any destructive or any disassembly. And all of a sudden we saw that there was this outside in bending of the electrodes and device components coming from the keyboard side of this device. And on top of that, where you see that yellow arrow, you see this high density feature. And once again, that's what, if you remember the last example, that's the kind of thing that we're looking for always in this investigation. Like, is there something there that could have been is that telling us something that we should look further? And that's what was the case, that with that information, we were able to direct the destructive testing. And in this case, we were able to find a location with this raised and thickened edges, and it was just pure copper. Once again, the EDS proves very useful because now we are knowing that this is a point that got over 1,000 Celsius, which also tells us that, that is consistent, putting all this story together with some type of mechanical damage through the keyboard, puncturing the cell and causing a cell short at that location where we're seeing that the end of that puncture. So once again, the destructive is there the non-destructive tells you where to look. The destructive really provides you additional information to corroborate your hypothesis. And so the next example actually plays very well with the previous talk, because this is a case in which we're not looking at high density features, but we're looking at low density features. And in this case was a batch of loose cells that was having an abnormally high rate failure when they were being put into use later in their lifetime. They were put into devices and they were failing. There was not a lot of clear understanding of what was the storage conditions of these cells. And when we looked at a non-incident cell, we all of a sudden found these low density features right at the copper current collector. So once again, that guided our investigation into cell teardown. And in this case, you could see with an optical microscopy that there were holes. And like I said, the previous talk was perfect because that showed the type of copper dendrites that can be formed. And what we were seeing is the holes were due to cell over discharge. You were dissolving the copper, and then if you were to cycle that cell, you could get those copper dendrites that were shown in the previous talk that can short the cell and produce failures. So once again, that the non-destructive tells you there's something to look further. Sometimes it's enough, but more often than not, you do want to follow up with some type of destructive testing to really dig deeper into the details to understand the failure mode and to make your product safer. Speaking of that, using usually the information from a failure investigation or just due diligence from a quality assessment, there's a lot of things that both the non-destructive and destructive techniques can teach you. So not to belabor the point that CT is a fantastic technique, and there's been a lot of advances on fast CT scanning of batteries, so you can get information out of them and get information about their alignment, how they look inside, and everything. But there are certain things that also can be enhanced by also complementing that with destructive testing. For example, getting a good sense of what your tab connectors look like, your insulation, what your tab welds look like, and particularly where the insulating tape looks like on top of, because those are things that are a little bit harder to detect purely with non-destructive techniques. And speaking of that tape, for example, here's an example on the left of what happens when the tape is not properly aligned, and all of a sudden that left bare aluminum exposed. And there's been a lot of research lately about what are the potential scenarios that are more likely to lead to thermal runaway, and usually having bare aluminum is one of those conditions in which could lead further down the road to a thermal failure. Similarly, you could see maybe at the edge of the electrode, the one to the right, also bare aluminum. And once again, understanding how those are things that might not be as easy to detect purely from non-destructive. So it's complementary, right? You do both things. On the destructive end, also there is a lot of value that you can get out of doing cross sections. So in this case are physical cross sections, but there were some great examples from the ion mills to do cross sections of cells, and you can get an idea of what your particles look like, of your current collectors, of your thicknesses. There's a lot of information to be acquired, and once again, this is just baseline understanding of what your cells look like. Now, and once again, this plays fantastic into a previous conversation about, how there's systems that can allow you to both detect the contaminant and then track it down. So these are two examples of finding the contaminants both in the anode and the cathode via non-destructive techniques. So one of the things that we usually do sometimes when trying to approach one of these things is to do cross-sectioning and then polishing to using the CT. We have a good sense of where is it located on the cell, and then we can do cross-sectioning and then polish towards finding the feature of interest. This is a slightly different example in which all of a sudden, when we were doing a cross-section analysis, we found silicon on the negative material, which there are many cells that have that in their formulation, but sometimes it happens that when a cell manufacturer changes from one batch to another, they might, if the batches are not properly clean, you might end up with silicon on a cell that was not designed to have it. So those are things that, destructive testing could, it's very useful. And, with this cross-section is very useful for understanding the distribution of said particles, whether if it's just a surface contamination or if it was something more like in the mix of the negative material in this case. But back to the examples of the loose particles, either by cross-section or by cell teardown and tracking them down, you can find the composition of those contaminants, and you can use that to inform and to learn more about what you can use that to track down the source of the contaminant. In this case, we have copper zinc alloy, and we were able to track that down into the factory, like where it was done, and finding that it was one of the slitting machines that was being used for this particular line of cells was not as sharp as it should be, and therefore was leaving some particles in the process. And that's kind of like, even beyond the destructive, the non-destructive and the destructive can further enhance, like, what is your action item? Well, you can also do a vendor audit and use this information to improve your processes, to identify sources of contamination, sources of misalignment, sources of, electrolyte degradation. You can do, I won't discuss it in this talk, but you can even do chemical analysis of to understand if there's a degradation process happening in your cells. So all of these things can let you then work together with your cell vendor to improve the process and make your products better and safer. And speaking of better performance, then we get to the last part of this set of examples, which is with battery performance evaluation. In this case, I was just discussing looking at the cells more on a kind of pristine status, right? Like this is as is, the quality, how they look like when they go into the system, into the device. But you also want to understand what they look like after they've been on the field. And there's a lot of cycling and reliability that goes into that. And, understanding if your material fractures and if you have a deformation of your windings, this electrode buckling that can be seen sometimes in some of the cylindrical models of cells. And this is where the non-destructive techniques are fantastic. You take your cells, you cycle them, then you look at them before and after, and you identify regions of interest. And once again, you can further complement that with destructive techniques. So going back to that example I was showing before, why you do the cross sections and look at the quality assessment of this, because then you look at a cycle cell and then you can do a side-by-side comparison, and all of a sudden you identify that right at that you find now a low density layer that is rich in oxygen that is happening right on on the surface of the negative, like right next to the separator. So that was something that we were able to identify doing a comparison before and after, combining cross-section CT, cross-sectioning, and SEM EDS mapping. So very powerful. Another aspect, and also it was like nice to see in the previous talk, like this whole discussion about understanding in air-free conditions, is just doing cell teardowns of cycle and uncycle cells, because that's where you can, once again, guided by the CT scanning, you can then see if this is a cell that's worth doing a teardown at 100% state of charge, because that's where you will be your potentially worst case scenarios, is when you are fully charged, as opposed to if you discharge the cell before unrolling it, like sometimes you might lose some information. That actually was the thought process we had back in 2020 when we prepared this paper on prismatic cells. We were observing some gaps in the as-made cells, but we also hadn't realized that as you were cycling the cells, you were able to, those gaps became bigger. And as those gaps became bigger, you started to see these low density features consistent with electrochemical deposits on the cells when fully charged. Now, once again, the non-destructive tells you that this might be a problem, but you need the destructive testing to really push a little bit further and understand better what was happening. And in this case, what we did was, once again, 100% cell teardown, air-free transfer, and because of the air-free transfer, we were able to see this dendrite-like features consistent with lithium plating and the growth of lithium dendrites on the surface of the separator. This is the separator mated to the negative, and with this is on the negative, but that you can see in the image to the left, that's on the separator. You see those same features. And once again, the talk before mentioned about how dendrite growth, in this case lithium, like the previous talk was copper, but lithium too, can cause a cell short and can cause degradation of either worse performance through micro shorts, or it can lead to thermal runaway if it's extensive enough. So and this was something that if you had done the transfer, first of all, if you had done you had not done the air-free transfer, the morphology would change upon exposure to air, so you would not be able to see the dendrite morphology, which is what is the main concern from a safety perspective. And then for my last example, and once again, going back to this cylindrical cell buckling, I mentioned CT scanning as the non-destructive technique, but there's a lot of characterization that can be done through cell cycling. It's just the capacity check, of course, but there's EIS, there's DCIR. There's a lot of things that you can extract of information from your cell's health through the cycling process, and that's yet another piece of that puzzle that, combined with CT scanning, can lead you to identify cells that are not performing well. In this case, we were seeing these 5 cells that were nominally they were different vendors, but nominally the same on paper on their capacities and sizes and characteristics. But when we were cycling them, we saw very different performances, with some of them actually having a very large dip in performance very early on. That's the red case. But all of this because of this buckling type of situation, that buckling that was happening in the inner core of the cells. And once again, this is important. You could tell that the performance is not doing it. It wasn't working as you expected. There's a problem. But where the destructive testing can take us one step further than that, and in that case, for example, showcase that through a cross section, you can see that the separator at the very center was actually being compressed. And once again, going back to that, what are the aluminum touching other sides on the negative could result in potential thermal runaways. And in this case, your separator has just been compressed to a much smaller amount. So once again, that there are plenty of destructive and non-destructive techniques that can be evaluated. But in the interest of time, I won't go over all of them. But if there's a lot of value in both doing the non-destructive and then pushing it one step further via a lot of the techniques that are being available nowadays and that are constantly evolving. So with that, I would like to thank you all for your time, and please feel free to reach out if you have any questions, or I look forward to discussing further during the Q&A section of this webinar. So thank you very much. Have a great day.
Thank you. Thank you to the audience for joining me today. My name is Sudhir Dahal, and I'm excited to present you on the topic of harnessing vibrational spectroscopy for battery component characterization and analysis, where I'll give a brief overview of vibrational spectroscopy technique, but more focus on the Raman spectroscopy. Vibrational spectroscopy encompasses a range of techniques that provide detailed insight into molecular structure and composition of materials, which is obviously crucial for advancing battery technology. Following that general introduction, I'll, like I said, go into Raman spectroscopy, provide some of its benefits, and then really do a deeper dive into principles of Raman spectroscopy, its advantages, and why it can be an indispensable technique for battery component analysis. Finally, in my final part of the presentation, I'll illustrate practical applications or use of Raman spectroscopy. These case studies will demonstrate how Raman spectroscopy can help in material ID, diagnosing the issues, and which will ultimately contribute to development of more efficient and reliable batteries and safer batteries. Again, thank you for joining. I look forward to exploring this topic with you. So, as many of you may already know, vibrational spectroscopy can be defined as these three prominent techniques: Raman spectroscopy, Fourier transform infrared spectroscopy, or simply FTIR spectroscopy, and near IR spectroscopy. Each of these techniques offer unique advantages that make them highly effective for analyzing battery components. So, however, commonly speaking, here are some of the attributes that they bring to the table, right, which is very much relevant to battery analysis. These techniques are non-destructive. They do not alter or damage the samples. Allow for further testing and preserve the integrity, saving cost and safety. It also requires minimal or no sample preparation, being spectroscopic technique. Sample states, different types of samples can be used, such as solid, liquid, and gas, and often without any sample prep. Results are rapid, within seconds or within minutes, depending upon your analysis. In terms of application, these techniques, bring to battery and battery component analysis. They're used for a variety of things, such as material identification, structural analysis, degradation analysis, electrode, anode cathode analysis, electrolyte characterization, and analysis of surface chemistry. So, having provided an overview of various vibrational spectroscopy technique and their applications in battery component analysis, let's now focus on Raman spectroscopy, which, as a technique, has now become particularly prominent and valuable in this field. It offers several compelling advantages, and the measurement technique it encompasses include macro or bulk measurements of bigger samples, quick analysis, microscopic measurements. So when they're looking at micron level details, the Raman microscope is a perfect tool for that, as well as Raman process measurement. These versatile techniques enable Raman spectroscopy to be applied in a variety of critical areas, such as providing getting information from structural changes, very sensitive information from structural changes, simultaneous measurement of multiple species, real-time measurement. Again, as I mentioned earlier, non-destructive analysis, which is really a big attribute that Raman spectroscopy brings. Ability to measure through container walls and windows. Again, this attribute ensures safety as well as sample integrity, and utilize enough Raman spectroscopy for these kind of things for research and method development. Being a very reliable technique. So in the next few minutes, I'll present the powerful insight that can be derived from Raman spectra in a clear and concise manner. I do understand while some of you may already be familiar with this information, I believe it will serve as a valuable review to underscore the capabilities of this technique, Raman spectroscopy. At the center of the slide, as you can see, you'll observe a simple curve with a peak that serves as an illustrative example. So beginning with the bottom image shown by the red arrow, this highlights the importance of peak position along the x-axis. The location of various peaks on the x-axis provides critical information regarding the molecular structure. In essence, the appearance and positioning of these peaks are instrumental in sample ID or molecular identification. Now, at the top, the spectral illustrate the relationship between intensity, which is shown in y-axis, and concentration. An increase in intensity corresponds to higher concentration of the substance and vice versa. Shifting our focus to the right, the set of spectra emphasize the significance of spectral bandwidth, which is crucial for determining crystallinity. Narrow bands are indicative of crystalline structure, while broader bands, as shown here, suggest an amorphous structure. Lastly, the spectra on the left demonstrate subtle shifts in peak position within the sample, within the same sample, really. These shifts are indicative of stress and strain within the material. By analyzing these various facets of Raman spectra, we can attain a comprehensive understanding of materials' properties and behavior, using simple examples like shown here. Now shifting our focus, I'll provide a few examples of how Raman spectroscopy is utilized in battery component analysis. In my first example, shown here, I'll highlight the critical role of Raman spectroscopy in the quality control of separator layers in lithium-ion batteries. The separator layers is, as the name suggests, is essential for preventing the anode and cathode from coming into contact and causing a short circuit. Ensuring the quality of these thin films is crucial for producing durable and reliable batteries. As shown in the slide, Raman spectroscopy can be employed to image the separator membrane, enabling us to access its condition and detect any potential damage that could lead to battery failure. In this particular test, as shown in the images here, the results were obtained as followed. It was a tri-layer separator membrane that was confirmed to have PP, PE, and PP, which is polypropylene, polyethylene, and polypropylene again structure. However, although those were as expected, it was determined that thickness of each layer was only 5 micron approximately, which is actually thinner than the standard requirements for optimal operation. So the message here is, the seemingly simple application demonstrate the immense power of Raman spectroscopy to analyze critical components, which thereby contributing to the creation of better and safer batteries. Now on to our second, next example. Raman spectroscopy is highly effective for analyzing both graphite and graphene. I'm sure a lot of us have heard Raman spectroscopy for graphene and graphite analysis. Quick overview: graphite is a multi-layer structure composed of graphene layers and is commonly used as an anode material in lithium-ion batteries because of its excellent ability to intercalate lithium ions, high electrical conductivity, and stability during charge and discharge cycles. So these properties are crucial, dependent on the integrity of graphite, making its analysis really essential for ensuring optimal and safer batteries. Graphene, being the single layer component of graphite, provides distinct Raman spectral information that can be used for detailed analysis. As you can see here, notably, there is a linear increase in the intensity of G band with the number of graphene layer in the Raman spectrum. As illustrated here in the slide, the G band intensity in the Raman spectrum is higher in graphite compared to graphene. Additionally, the peak shift in the G band can indicate the number of graphene layers present in the graphite. Therefore, by analyzing the G band itself, it is possible to determine the number of graphene layers in graphite sample, all using Raman spectroscopy. Another significant aspect of Raman spectroscopy is its ability to identify single-layer graphene through the intensity ratio of the 2D band to the G band, as shown here. For instance, when the intensity of 2D band, also known as the G prime band, intensity ratio of 2D band to the G band is 2, it indicates that the presence. It does indicate that there is a single layer graphene present. So again, these seemingly Raman spectrum can be really powerful in giving that kind of information. So on the left side of the slide, you'll see a Raman image of graphite electrode grown on a silicon substrate under experimental condition. This image was created using raw spectral data, such as those described earlier and shown on the right. The image can be used to visualize presence of single layer graphene, multiple layer graphene or graphite, defects, and the silicon substrate itself. Raman images like this are extremely powerful tool in all stages of quality control, research, and product development. Now, shifting our focus to the cathodes of lithium-ion batteries. In the next example, it is important to note that lithium compounds are commonly used as cathode materials. For instance, lithium cobalt oxide is widely employed as a cathode material in lithium-ion batteries. Despite its advantageous properties such as high energy density and stable cycling performance, its electrical conductivity is relatively low compared to some other materials. Additionally, it is also quite expensive. As a result, extensive research is being conducted to identify alternative lithium compounds that can offer high performance at a lower cost. One such lithium compound is lithium iron phosphate, also commonly abbreviated as LFP. Now, although its inherent conductivity is very low, when combined with graphene, its conductivity is significantly enhanced. In this example, we demonstrate the identification and characterization of lithium iron phosphate. The spectrum shown here was obtained using the all-in-one process Raman analyzer with the characteristics peak highlighted by the blue arrow. So Raman analysis, as shown in this example, allows for monitoring of specific species by examining peak positions and other characteristics of spectrum. It provides these results almost instantaneously, right? Often within seconds or minutes. And the rapid feedback facilitates quick monitoring and implementation of corrective actions, which can ultimately lead to significant savings in cost, time, and resources. Furthermore, chemometrics and advanced data analysis techniques are frequently employed to achieve more accurate results from real-world samples, which are often complex in nature, like the one discussed here. Really talking about real-world samples, manufacturers often aim to create active materials, slurries, or mixers, right, with a lot of things. To facilitate this, a basic chemometric model was developed to quantify the level of lithium iron phosphate in the powder form, and then the level ranged from 90% to 100%, all using the all-in-one Raman analyzer. This analyzer, equipped with a 785 nanometer laser, was able to rapidly gather spectra and conduct the model in a matter of seconds. The acquisition parameters and conditions are detailed on the slide. As you can see here, and as demonstrated, utilizing this model allows for quantification to be achieved within 50 seconds, underscoring the remarkable efficiency of Raman spectroscopy in terms of time, cost, and resource savings. At the top of the slide, you can observe specific spectra corresponding to various concentration of lithium iron phosphate, and the model that I just mentioned. The model performance indicates that the chemometric model really effectively operates within these concentration ranges, as shown in this graph. I don't want to go deeper, but just to give you a quick example. So to enhance the robustness and extend the range of model, additional data is always preferred, and it can be incorporated as needed to further refine the model based on the need. Therefore, the process Raman analyzer has demonstrated its capability to monitor and quantify the concentration of lithium-ion phosphate, which is an important compound for lithium-ion battery manufacturing. And using this type of solution makes Raman spectroscopy really a valuable tool for analyzing components such as this. That concludes the key examples of Raman spectroscopy for battery component analysis. Before we end the presentation, I'd like to highlight our extensive analytical instrument portfolio. As shown in the slide here, we offer a comprehensive range of laboratory chemicals, including fine chemicals, solvents, and standards to support battery research, development, quality control, and manufacturing scale-up. All right, with this, we have come to the end of my presentation. Next up is the Q&A session, and I look forward to answering your questions in that section.
Yeah, thank you very much for this great presentation. We will now continue with our Q&A session. So for everyone who hasn't submitted their questions yet, now is the time to do so. Ask everything you want to know about battery research to our three experts. I can see, now we're complete. Perfect. Thank you very much. So we will start with the first questions that already came in. So Weihui, that's one for you. A metal particle in the cathode could lead to a short circuit. Do you have solutions for detecting metal impurities in cathode material? Could you explain more about the solution?
Okay. Yes, we do have a dedicated metal impurity detection solution named Particle X. This is an automated SEM EDS solution, which can automatically and rapidly identify, analyze, and statistically classify impurity particles for cathode material, and then providing customer with rapid, accurate, and reliable data, and also a one-click report for the result for battery customers to do QC quality control for cathode material impurity control.
Great, thank you very much. So, Hernan, in your presentation, you talked a bit about thermal events. If users were to experience one with their batteries, how can they go around and perform a failure analysis investigation?
Thank you. That's a great question. So, and probably as you saw from my talk, failure analysis investigations for batteries usually require specialized equipment, such as a CT scanner or like an SEM EDS. So that means that you should always try to coordinate with, if you have the internal resources, with your appropriate FA lab or research lab, but usually you do need some expertise to try to interpret those results. So if you have an FA team, definitely contact them, or you can contact folks like just myself or other outfits that do the same type of analysis. And one disclaimer is that once you've had a battery fire, you do need to follow strict regulations about how you ship those batteries. So there's options on the market, and if you're ever in that situation, feel free to contact me. I can put you in contact with people, but there's a lot of issues about how you can send your burned battery to a place that has the equipment to do the analysis. So thank you.
Perfect, thank you. So Sudhir, you showed an example of the thin film layer Raman analysis, and one of the questions that came in is, how long does the typical measurement like this take?
Thank you for the question. Yes, if I look back at that particular example, it has about 5 micron layer thickness of 3 materials, and then approximately, that would be 15 microns and approximately 15 on both sides. So, we're looking at about 45 microns deep measurement, and depending upon the resolution and quality of data needed, I think you can get a very quick measurement within a couple of minutes. But if you need a slightly higher resolution data for this one, I would say within 10 minutes is a reasonable time.
Perfect. And I also have another question for you. I have the Thermo DXR microscope with a 785 nanometer laser. My understanding is that you offer other lasers that I can change out as needed. How do I know which one will give me the best data?
Great question. And yeah, we do get this similar question a lot for Raman analysis. So the DXR microscope from Thermo, it it allows customers to change their own laser. So it is consumable that can be bought, and the old one or the one that has died can be changed with the new one by the customer. No additional service actions are needed. With that said, you seem to have 785 nanometer laser, and I'm sure it was chosen based on the typical samples that you analyze. But I would say choice of laser, optimal laser, depends upon your sample. So if your sample is generally highly fluorescent, then you would want to avoid more wavelengths or laser on the visible regions, such as 530, 532, or even 633, right? Um, However, if your sample is not as fluorescent, the lasers that are on the shorter wavelength than 785 are the best choice. So there is no easy answer. It really depends on your sample, and even within a sample, the constituents can give out fluorescence and so on. So the good thing is that you can always add your own laser and change it out, and even based on your sample, you may need to change the laser in a daily basis, right? So maybe just keep a couple handy if you can, and see which one is best for your sample.
Yeah, of course. Thank you so much. So we're coming back to examples involving cell cycling, and on that you showed, you presented a couple of techniques. Are there any other techniques beyond the ones you described?
Yeah, no. And once again, in the interest of time, I think I already ran long enough on my part of the presentation, but there's a lot more that you can do beyond just the teardowns, the cross sections, and the CT. There's a plethora of, well, first of all, materials characterization, like, that Sudhir was presenting. And so there's a lot of other things that you can do. Of particular interest, something that we found recently that has added value to our clients has been running a chemical characterization, sometimes on the electrolyte, to detect any type of changes over time as upon cycling. Those are a little bit of somewhat involved experiments, but they can provide a lot of insights into the performance of the cells. So that's another characterization technique that I didn't cover.
Perfect. Thank you so much, Hernan. And Sudhir, I'll come back to you with another question regarding Raman. I need a Raman probe that withstands certain experimental condition. Could you explain more on the use case where I can check if you offer the one, or where can I check if you offer the one that will work for me?
Sure. Yeah. So with the Mark Matrix all-in-one from Thermo Fisher, we offer a variety of probes, and there are what we call standard ball probes, and there are reaction probes, and different varieties depending upon your experiments, upon your sample condition, your laboratory conditions, and so on. I think the two best ways would be to go to our website. If you simply type Thermo Fisher all-in-one probes, on a search engine, you'll get to the website and see for yourself what are the available options, and if one or more can fit your need. The other option is obviously reach out to your local sales or application colleague reps from Thermo Fisher. And if you're even having more troubles on that, maybe just let us know through the chat, and we'll be happy to guide you to the right person depending upon your reason.
Perfect. Yeah, thanks for these recommendations. Weihui, I'll come back to you. And could you please let us know if CleanMill can be used to analyze solid-state electrolyte for sample preparation and use SEM for imaging?
Good question. I would like to say yes. And our CleanMio system are indeed fully compatible with our Clean Connect sample transfer system, which should be designed for air-sensitive samples and achieving a complete argon inert gas sample transfer workflow. And this capability ensures rapid and straightforward sample transfer from the CleanMio system to the microscope to the electron microscope chamber, minimizing the time from sample processing and making it possible to observe the material in their native state. So usually the solid state electrolyte is air sensitive, so we can totally protect the air sensitive solid state electrolyte and observe the microstructure in SEM. Yeah, this is the answer. Thank you.
Thank you so much. Okay. I know there were several more questions that came in. So for all the questions that we couldn't get to today, we will, your speakers will reach out to you via email to answer your questions. And with that, I would like to wrap up this session, but not without thanking our three amazing speakers for today. And also, of course, to remind you that this Building Better Battery series will continue on the 3rd of December with a talk on enhancing battery R&D and manufacturing via advanced data management and interpretation. So make sure you will join us again then. Thank you so much again for everyone who joined. A special thanks to our speakers and have a great rest of your day.